Today, on how it's made. Springs, the unsprung heroes of industrial machines. Pavers, we bring you a report from the street. And pianos. We'll lift the lid on the making of a grand piano in a special two-part report. A spring is a flexible metal device that returns to its original shape or position after it's stretched, squeezed, or twisted. Springs were first used in clocks during the 16th century, and starting in the late 1800s, in chair seats and bedding. Today, springs pop up all over. They're crucial components of modern technology. Different types of springs include compression on the right and extension on the left. During use, these torsion springs will twist at one or both ends. Workers start with rolls of steel cord. The cord diameters range in size depending on the type of springs being made. A machine called a de-reeler unwinds the roll, feeding it to a computer-guided forming machine. This forming machine forces the cord through a channel, shapes it into a coil, and then cuts it into segments. Small wheels and a metal shaft guide the cord into shape. These are torsion springs for use in the automotive industry, which relies heavily on a variety of springs. The average car, for example, has about 350 of them. A cone-shaped yellow sensor detects the correct angle of each spring. A good reading is required, so the machine can move the next spring forward through the channel to be formed. This machine can produce up to 2,000 springs per hour, depending on their size. Here, another larger forming machine creates extension springs that are nearly 16 centimeters long. A mechanical arm grabs the coil and chops it into segments after it's formed in a channel. As the coil emerges, another mechanical arm steadies it to prevent it from vibrating. This keeps the spring's tension constant, enabling the machine to produce at top speed. In slow motion, you can see how the machine grabs the coil's first ring and bends it to form a hook. This all takes place as the coil emerges from the channel. A vise then secures the last ring on the end of the coil, while another arm twists it to make the spring's other hook. Slowed down, you see how two arms surround the coil being held in the vise. One arm then grabs the last ring, while the other arm twists it upward. This machine makes compression springs, a model with tapered ends that's often used in seat belts. A metal probe detects the correct length of the springs after they're formed. The machine has 4 rotary shafts called cams. A computer ensures each spring has the desired specs. The springs are also heated to relax the metal. This gives them the ability to retain their shape after flexing. Another machine creates longer, thicker torsion springs. It shapes the cord into a coil with a shaft and then passes it over a tube to steady it. This ensures the spring will have the required tension. Springs can be as thin as human hair or as thick as a broom handle. Train wheels, for instance, include some of the industry's thickest compression springs. This machine makes another type of spring, often called wire forms. They're flexible steel cords curved or bent at an angle. These ones, shaped like a W, are used in ovens. Here, a worker places a spring into a machine that makes its hooks. He uses an adapter to avoid hurting his fingers. He places each one individually because specs for springs can vary by minute amounts. This company makes some springs with hooks made of 2 rings instead of 1. Clients order them this way because the hooks are more durable. Custom orders for springs can range from just a few to many thousand. This is another type of wire form. It'll be used in a firearm. A worker assembles it by hand because it's so intricate. After joining 2 base pieces, he places them into a small die. Using a foot pedal, he controls the die to bend the segments and complete the assembly. To check the compression spring's tension, a worker tests it with a weight gauge. The correct tension varies depending on what the client wants. A 3.8 centimeter long spring, for example, might need to withstand 5 pounds of tension when compressed to 2.5 centimeters. To test an extension spring, workers just add hooks to the weight gauge. Whether they're extension, compression, torsion, or wire form, and whether they're inside pens or satellites, springs prove that some old ideas definitely still work. You could say that interlocking concrete pavers came out of the rubble of World War II. In post-war Holland, there weren't enough clay pavers to rebuild city streets, so the Dutch began making concrete pavers. The Germans refined the technology and exported it to North America, where they found a quick road to success. Call it a concrete solution for paving. These pavers are solid, and the interlocking design disperses weight, easing the load on the road. To make these pavers, a conveyor belt delivers concrete sand to a weigh belt that weighs the coarse sand as it falls onto it. The weigh belt carries the sand forward, while another conveyor belt unloads stone chips to be weighed. These chips are no larger than 1/3 of a centimeter. The ratio of sand to stone chips varies, depending on the type of paver being made. The weigh belt transports the stone chips forward, along with the coarse sand. Both are en route to the skip hoist. They spill off the conveyor into the skip hoist, which is essentially a bucket on rails. Cables pull the loaded bucket upwards. It stops about 9 meters up, just above a big concrete mixer. A trapdoor opens and dumps the sand and stone chips into the mixer. 6 giant steel paddles mix and then rotate and mix again, while cement is added automatically through several nozzles on the side of this enormous mixing bowl. Making pavers is a bit like baking cookies. Too much or too little liquid in the batter, and it won't bake properly. Water is added until the consistency is just right. Nozzles also shoot a pigment into the mix to tint it. The mixture looks dry and crumbly, but the recipe gives it just enough moisture to form the concrete. Now a filling wagon spreads the mix over a steel mold containing up to 50 paver-shaped cavities. The mold press head applies 10 tons of vibrating pressure. This pulsating force compacts the mixture into the paver mold and removes any air pockets, which could weaken the pavers. Hydraulic cylinders lift the mold, leaving the pavers on the press board. The press board slides out and the mold once again gets filled in and makes another 50 paver stones. It only takes about 10 seconds to mold, compact, and release a batch of pavers. The press boards filled with pavers slide into a rack. A hydraulic chain hoist lifts each board into a large holding rack. There, a special moving wagon called a finger wagon picks up all the boards from the rack in just one move. The electrical wagon moves along a rail to a curing kiln, where it's almost 38 degrees Celsius. The pavers actually generate the heat due to a chemical reaction from the combination of cement and water. About 12 hours later, the finger wagon carts the pavers out of the kiln. They're now 70% cured as a result of the chemical process that binds the cement, sand, and gravel, causing the pavers to harden. The rest of the curing will happen over the next 28 days. The pavers are now sturdy enough to handle, so 4 steel arms with rubber pads move in and straighten the stones on the board. These alignment arms are hydraulically driven. They arrange the concrete pavers so they interlock snugly. Now, hydraulic clamp arms lift the pavers off the board and begin to pile them up. they're making a cube of stone. This stacking machine is called a cuber. It packs 9 or 10 layers of pavers on top of one another to make this cube. The cube is actually called a bundle. It will be strapped and shipped out to the job site. These concrete pavers will be on the road soon, in more ways than one. We still say tickle the ivories, even though ivory isn't used to make piano keys anymore. It's banned to protect elephants who were killed for their ivory tusks. Pianists now tickle the plastic. But the techniques involved in manufacturing a piano haven't changed much and still rely on hand craftsmanship, just like a century ago. Beautiful music is a triumph, but so is the piano itself. Made of inner and outer rims, a soundboard, treble and bass bridges over which the strings are stretched, and a heavy cast iron plate. To make a piano rim, automated rollers spread glue onto sheets of hard rock maple, coating both sides. Then they layer the glue-soaked sheets 5 to 8 deep, depending on the model of the piano. Workers feed the wet layers of wood to a rim press. An impact wrench, powered by compressed air, turns the clamp screws. The screws bend the wood into a piano rim form. They measure the pressure on the layers with a torque wrench. Steel arms reach across the wood, holding the shape while the glue dries. After 24 hours, workers loosen the machine's grip, and the rim now holds its contour. Now it's into what's called the conditioning room for more drying out. The piano rims stay in this warm, arid room for 30 days. It's time to make the bracing structure. They place glued struts inside the rim, then apply pressure with a clamp. The framework remains in this embrace for an hour while the glue dries. This piano will also have a tension resonator for extra support. Steel turnbuckles attached to a center hub. A worker tightens the turnbuckles with a wrench. Then he thumps it to make sure it's tight and won't rattle. Next, they'll install the soundboard made of spruce and the 2 bridges. Strings will straddle the bridges and transmit vibrations to the soundboard, which is the amplifier of the piano. A worker glues ribs onto the soundboard. He lowers wooden clamps over each rib to apply pressure while the glue dries. That takes about an hour. Next, he thins the ribs around the edges with an automated stagger tooth shaper cutter. This will allow the soundboard to resonate freely when the piano is played. Now they position the soundboard in a bridge press. Then they place a bridge locating fixture on top of the soundboard. This device holds the bridge in place while it's glued to the soundboard. After the 2 bridges are glued down, they lower the soundboard onto the piano rim. They hoist a cast iron plate onto it. It's a critical fitting. If they don't get it right, the piano will never function properly. Then the plate is removed for finishing. A worker cuts notches in the bridges, which are now topped with a lubricant. This very sharp chisel cuts through the hard maple like butter. Each notch will cradle 3 piano strings, giving them the freedom to vibrate. Now they roll glue onto the outside case of the piano, which is made of rosewood veneer on maple. They fit it snugly over the rim structure. A mechanical clamp holds it in place for an hour while it dries. Then they stand the entire piano on its side. spinning cutters shape the arms that sit next to the keyboard into an elegant curve. This is called a vertical stroke sander. A worker runs it along the side of the piano to smooth out the wood. After a black polyester paint is applied, they buff it up with this electrical cloth polisher. Then they hand rub a mirror glaze cream into it until you really can see yourself in this half-finished piano. Raw talent and deep pockets. That's what a budding pianist needs initially, because a grand piano can cost about the same as a luxury car. And, like a luxury car, when you lift the top of a grand piano, you'll see that a lot has gone into its construction. The bass and treble bridges are now fixed to the soundboard of this half-finished piano. To add glamour, they spray gold paint on the cast iron plate. The next step involves the pin block, which holds all the stress. It bears 45,000 pounds of tension from the strings and transfers it to the iron plate. He drills into the maple pin block through holes in the iron plate over it. The holes are for the tuning pins, hence the name, pin block. They unfurl pieces of steel wire from big coils. Using a vice grip, the worker twists the end of the wire into a neat loop. Then he hooks it onto a hitch pin on the back side of one of the bridges, making sure it runs between the guide posts over the bridge. Now he threads the wires through another guide, called an agraffe. Using wire cutters, he snips the wire to the exact length that he needs. Then he wraps the wire on a tuning pin, using a device called a stringing crank. He taps it into a hole in the pin block. Then, using a pneumatic hammer, he drives the tuning pins into the pin block. Now the string stretches from above the bridge to the pin block. Each string is under a tension of up to 425 pounds. Again, a force that will be kept in check by that heavy cast iron plate. Now he places little felt-covered blocks called dampers above the strings to stop them from vibrating when a note is played. Using pliers, he makes parallel bends in the damper wires so they're aligned. He pounds the keyframe, checking for gaps that could cause knocks under a pianist's vigorous blows. He smooths out the gaps, shaving off bits of wood with a strip of sandpaper attached to a handle. Now another worker presses the piano keys in between steel guide pins that have been installed in rows on the keyframe. She uses an air cylinder to push the back check into the end of a piano key. The back check is a piece of wood covered with felt and buckskin that will catch the piano's hammer after it strikes a string. It's time to make those hammers. She glues the felt-covered top onto a thin piece of hornbeam, a species of very strong wood. When a pianist hits a key, it will catapult the hammer into the string, and that produces a note. Now she aligns the hammers to be perfectly parallel, using a plastic square as a guide. This is called squaring it up. Next, she sands the tail of each hammer with a file, so there'll be no sharp edges to damage the back check. Then she attaches the hammers to the top of the keyboard with screws. Now she places weights on each key and then gently taps the rail to get the hammers moving. She's testing the amount of effort it would take for a pianist to push each key down. This is called the weigh-off. After she determines how much weight is needed, she marks a place on the side of the key and drills 1 or 2 holes. She plugs each hole with a piece of lead. In a process called swedging, she pushes a divot into the lead so it expands and fits snugly into the key. The lead will counterbalance the weight of the hammers and give the key the required amount of weight. Next, this technician checks each hammer and each key making subtle mechanical adjustments so they move smoothly and fluidly. It's the piano's first big tune-up. He fine-tunes the hammer action by using a let-off tool to adjust the driving mechanism. The piano is now ready for the hands of a skilled pianist and the ears of an appreciative audience.
Deep. Sanitary napkins. Find out the secret to their absorbency. And concrete pipes. A report from the underground. The term robot comes from the Czech word robota, which means forced labor. Most robots are designed for repetitive work that's difficult, dangerous, or would just bore human beings to death. Robotic arms have varying degrees of freedom, meaning they can pivot in different ways. A robotic arm resembles a human arm. It has a shoulder, an elbow, a wrist, and a hand. The shoulder is actually a stationary base to which the rest is attached. An engineer first designs all the parts on a computer. Then, those plans go into action. To form the base's outer casing, they bend steel sheeting into shape using a computer-guided press. Next, they paint the casing in powder paint using an electrostatic process that guarantees a thorough, even coat. They run a negative electrical charge to the casing and a positive charge to the paint particles. This makes the casing draw the paint to it like a magnet. Once the paint on the base casing dries, they use silkscreen printing to apply what's called the user diagram. It illustrates which parts move where and how. Now they build the robotic arm's hand called the end effector. Robots can be outfitted with all sorts of end effectors. Here they're making a gripper whose two claws come together to grasp and carry objects. To make each claw, an automated metal drill cuts a groove lengthwise and widthwise in a piece of aluminum. They assemble the electrical circuit board that will later go inside the base. The robotic arm's 6 separate motors will plug into it. Next, they assemble the mechanical parts of the base. First, the motor that makes the arm rotate. Then the gear that goes on the vertical shaft holding the robotic arm upright. When the motor makes the gear and the shaft turn, the robotic arm turns with it. At the arm's shoulder level, they install a system of 4 pulleys. Each consists of 2 plastic wheels on a separate axle with a rubber belt running between them like a clothesline. The belt has little teeth that grip grooves on the wheels. It rotates the wheels, making the robotic arm move. Each joint in the robotic arm is capable of and programmed for a specific range of movement. Like the human arm, the combination of these movements manipulates the end effector. They plug an electrical wire that links the gripper to the shoulder into a circuit board located in the shoulder. Then they screw the entire arm to the base. They link up the wires from the circuit board in the base to the motors in the shoulder. To do this, they have to bunch the wires, 48 of them in total, and thread them through the shaft that attaches the base to the arm. Once everything's connected, they fine-tune and test the gear and pulley systems to see if they run smoothly. Now they can install the gripper and the shaft and gear system that operates it. Turning the gear one way opens the grip, turning it the other way closes it. Now they mount the assembled gripper to the forearm, plugging its motor into a circuit board that they've already installed there. They plug the wires from all 6 motors into the main circuit board, which they then install at the back of the base. The robot controller, the brain that runs the arm, is a separate unit. It controls everything connected to the circuit. To move the robot, the computer inside the controller switches on all the necessary motors. It can control 8 motors, 6 in the robot and 2 optional accessories. You can program it to perform a variety of tasks. From start to finish, it's taken just under 30 hours to assemble this robotic arm. It can lift up to 4.5 kilograms, about the weight of a full-grown cat, and it can move at a speed of 2 kilometers per hour. Most robots are reprogrammable, meaning that to change their behavior, you simply write a new program. From an employer's perspective, robots may be the ideal workers. Granted, they have no ideas of their own, but their productivity is constant, they never call in sick, and they never take lunch or coffee breaks. Tattooing dates at least as far back as the Bronze Age. A 5,000-year-old body found in a European glacier had several tattoos on his skin. Archaeologists have even uncovered what they believe are Stone Age tattooing instruments, sharp bone needles and clay discs containing mineral pigments. Walk into a tattoo parlor and the vast selection of elaborate designs will astound you. Once you make your choice, the tattoo artist traces the image. Next, he places the traced image on carbon paper and retraces the lines. This creates a carbon outline of the tattoo on the reverse side. The artist will use this blueprint, as it's called, as his guide. He cleans the customer's skin, then firmly presses on the blueprint. The carbon image transfers easily because the skin is damp. Now it's time to construct the needles. Most tattoos require 2 needles, one to make the outline of the image, the other to shade and color it in. Each needle is made up of as many as 20 smaller needles. The artist aligns these small needles in a jig, then solders them together onto one end of a steel rod. There's an eye on the other end. The number of small needles in a needle depends on the tattoo design, how thick its lines are, how big its colored areas are. The finished needles go into an autoclave to be sterilized. That takes 20 minutes at precisely 170 degrees Celsius. The tattoo artist uses that time to assemble the tattoo gun. After cleaning the frame with rubbing alcohol, he installs the motor called the coil. When an electric current runs through the coil, it oscillates the needle at up to 50 times per second. Once the 2 needles are sterilized, he takes the one for outlining, called the liner, and slides it into the tattoo gun. He hooks the eye on the other end onto the spring. As the spring moves back and forth, it moves the needle up and down. The tattoo artist stops and starts it with a foot pedal, like a sewing machine. Time to tattoo. He turns on the power supply to 10 volts and dabs the needle in the ink cap. The gun sucks up the ink. Some petroleum jelly on the skin helps the needle glide more easily. He begins by tracing the lines of the blueprint. The needle punctures the skin at a rate of up to 3,000 times per minute, injecting microparticles of ink which intermingle with the cells of the dermis, the skin's second layer. The artist continually wipes away the excess ink to keep his work area clean. After finishing the outline, he reapplies petroleum jelly. This seals the pores of the skin and prevents bleeding. Then he changes to the other needle and begins shading and coloring the image with a back and forth movement. He applies one color at a time, overlapping them to ensure thorough and even coverage. The needle can penetrate from 1 to 4 millimeters, and a good tattoo artist knows just how deep to go to create the different parts of the image. For example, he has to inject the outline the deepest, but going too deep can tear the skin and cause excessive pain and bleeding. But not going deep enough misses the dermis and leaves marks after healing. The cells of the dermis are remarkably stable, so tattoos last a lifetime. This tattoo has taken approximately 45 minutes to do from start to finish. The area will dry and scab over. Then, the scab will fall off, and this body art will be ready for exhibition. Believe it or not, World War I led to the invention of disposable sanitary napkins. American nurses serving in France discovered that the bandages they used for the troops could double as very absorbent menstrual pads. This led the bandage company to introduce disposable sanitary napkins in 1921. Today's disposable sanitary pads are made of layers of cellulose combined with superabsorbent polymer powder. Polymer is a fluid-absorbing chemical derived from either petroleum or wheat. Cellulose is the fiber that makes up the cell wall of trees and plants. It also retains fluid. Pulp and paper companies grind and moisten it to form a product called pulp. Producing sanitary napkins begins with half-meter wide rolls of cellulose pulp. The rolls feed one long machine that does everything. First, knives spinning at 3,000 RPM shred the pulp into a fine fluff. Then the machine sprinkles that fluff with polymer powder. The polymered fluff then travels through what's called the doser, a device that measures out the required amount of fluff per pad layer. The machine then suctions each dose into a closed chamber where an air current blows it into a pad-shaped mold. Then another air current blows it out of the mold onto a wheel that transfers it to a conveyor belt. The machine simultaneously makes a second pad layer. This one is smaller, rectangular, and at least double the density of the first layer, meaning it has more cellulose compressed into a smaller size. The compression roller also embosses a pattern that will disperse the menstrual flow, helping absorption. This demonstration shows the critical absorption role the polymer powder plays. It can retain up to 40 times its volume. As the polymer soaks up the liquid, it transforms from powder to gel. Different types of polymers have different reaction speeds. This type absorbs at average speed. This will be a 2-layer pad. The number of layers and their weight depends on the degree of menstrual flow a pad is designed to absorb. Now the machine's conveyor belts merge, bringing the 2 layers together. Now the machine sandwiches the layers between plastic sheets. The top one is perforated to allow fluid to pass to the absorbent layers underneath. The bottom one acts as a leak-proof barrier. A roller stamps the contour of the pad, sealing the absorbent layers inside. Now the machine applies glue to a paper strip and to a pair of small paper rectangles. It slaps the strip on the back of the pad and the rectangles on the side flaps, called the wings. To secure the pad to underwear, you remove the paper to expose the adhesive. The pads are still connected to each other. A cutting die excises each one. Abrasive foam on either side of the die grips and pulls away the material surrounding the pads. A vacuum then sucks this excess away. Now the pads move on to the packaging line. The equipment first folds over the adhesive wings, then folds each pad in 3. The folded pads now go into plastic wrap. A hot iron-like device called an embossing press seals the plastic around each pad. Then a knife cuts in between the pads, separating them into individual pouches. Next, 2 belts sandwich the pouches and carry them down to the stacker, where an automated counter lines them up for packaging. As a vacuum opens the bag, a mechanical arm inserts the pads. The equipment then seals the bag shut. Everything you've seen happens at an impressive pace. From start to finish, it takes just 40 seconds to make and package a sanitary napkin. Most underground sewer and drainage pipes are made of reinforced dry mix concrete. Reinforced refers to the fact the concrete has steel bars inside it for added structural strength. Dry mix refers to the type of concrete. You can mold it, then immediately extract it, and it holds its shape. Concrete pipes can be as small as 25 centimeters or as large as 3.5 meters. It has a 100-year lifespan. Dry mix concrete is made of stone, coarse sand, Portland cement, which is a finely ground blend of clay and limestone, water, and a chemical that acts as a water reducer. Trucks unload the sand and stone into outdoor storage bins. The materials automatically drop onto a conveyor belt, which transports them to storage silos above the factory floor. The cement arrives by cement tanker, which blows it into a silo. All the silos feed the mixer. As the ingredients blend, the cement and water combine to form a paste that coats the sand and stone. The water reducer enables them to use minimal water. The less water, the stronger and more durable the concrete. Meanwhile, workers use a special machine to build what's called the cage, a circular steel frame that will form the pipe's internal structure, its backbone. They insert 2.5-meter-long steel rods in a circular configuration, pushing each rod partway through the machine to the other side. There, an automated spot welder fuses a steel cable to one rod. Then the machine begins turning, winding the cable tightly around the rods. Here, a worker is turning the machine manually just to show us the process in slow motion. This is what it looks like at the normal automated speed. As the rods pass through the machine, the welder fuses the cable to them in one continuous spiral. As the spiraled cable reaches the end of the rods, the machine's claws spread outward, forming a wider section on the end. This is called the bell section. Workers position it on a base ring designed to hold the cage in place. Then they close a hinged steel mold over it. Now they're ready to pour the concrete. A forklift transports the mold to a machine called the packer head. They position the mold directly under it. A long drill-like screw descends into the mold. As concrete pours in, the screw turns at high speed, moving up and down. Its blades propel the concrete outward against the mold walls, forming the pipe. This process is called centrifugal projection forming. The process for making large diameter pipes is slightly different. A welder fuses spacers to the cage, both inside and out. These will center the cage inside the mold. Workers position the cage onto a base ring, then lower the outer part of the mold, called the outside form, over it. After securing it to the ring, They lower the unit over the smaller inner part of the mold, called the inside form. An overhead funnel pours concrete into the cavity between the two mold forms. Powerful electrical vibrators shake the mold. This forces the thick concrete downward, filling the cavity. This process is called vibration forming. With either pipe forming technique, the molded concrete is quite fragile, so the molds go off to the curing warehouse to harden. There, workers remove them, leaving the pipes standing upright. Steam hoses transform the curing warehouse into a sauna. The temperature rises to 60 degrees Celsius, the relative humidity 100%. The concrete hardens in about 12 hours. Concrete pipes buried underground have to be able to withstand the weight of the earth above them, so the company subjects sample pipes to extreme pressure to test their maximum resistance. Concrete pipes join together with watertight rubber gaskets.
Today on How It's Made. Inflatable watercraft. It's sink or swim. Couscous. The non-Italian pasta. Modeling dough. Creativity takes shape. And wicker products. The upside of being a basket case. Today's inflatable watercraft range from rafts and dinghies to canoes and kayaks. They're less expensive than conventional boats and easier to store and transport. You don't need a trailer, just throw your boat in the trunk, then unfold and inflate it when you get to your aquatic destination. Whether it's a raft shooting the rapids or a motorized boat gliding across a calm lake, an inflatable watercraft begins with sturdy, waterproof material. This company uses a millimeter-thick PVC fabric that has a nylon or polyester fiber core. After workers trace and cut out the pieces that will form the boat, they connect them with a strip of the same material, fusing them together using a machine with a propane flame. The intense heat melts the surface of the PVC until the pieces bond. Here's that bonding action in slow motion. Next, they fuse a strip of pure PVC to the underside of the joint. This ensures that air won't leak out of the boat where the pieces connect. Inflating the boat will pull on the material surrounding the air valve, so they reinforce that area with a round piece of PVC called a doubler. This high-frequency welding machine applies 127 kilograms of pressure and heat-generating FM waves to fuse the doubler in place. Then they cut a hole in the middle of the doubler for the air valve. Next come the cones. Cones support the weight of the motor and enable the boat to plane, to rise above the water when traveling at high speed. Using the propane flame machine, workers seal together the ends of the boat, then insert the inside cone piece just before they close her up completely. They finish off the seal using the high-frequency welding machine, then pull the cone piece through. They inflate the boat until the pressure forces the cone piece into place. They seal all around it with heavy-duty caulking. Stick on the outside cone piece, then screw it securely in place. They inflate the boat fully now to perfect the seal and to expel the excess caulking. Now they install what's called the transom, a plank of wood that supports the motor at the rear of the boat. They cover it in boat fabric, using a plastic resin-based glue that's resistant to the fiery heat of the sun. They apply the same glue to the piece of material that will become the underside of the boat, then position it in place. After gluing on a bumper made of hard PVC, they coat the boat's underside in a liquid plastic resin. This protects the bottom when the boat runs aground over rocks and sand. They test inflate the keel, a stabilizer that runs the length of the boat. Then they deflate it and begin installing the floor. The floor is made up of 5 connected pieces, 3 made of aluminum and 2 made of fiberglass, plastic, or wood. The hole in the floor is for the keel's air valve. After inflating the boat, they inflate the keel. Now they can take measurements to determine where to position the oars. First, they glue on the oar locks, the pieces that hold the oars in place. The oars are made of aluminum, so they're lightweight and they won't rust. The motor is 6 horsepower to 50 horsepower, depending on the size of the boat. Couscous is a traditional staple of North African cuisine. It looks like a grain, but it's actually pasta. These days, few people make couscous from scratch. Even in North Africa, they usually buy their couscous ready-made and just steam cook it. Couscous is the product of culinary simplicity. It's made from one ingredient and one ingredient alone: wheat. Most often, the durum species of wheat. When you remove the grains, grind them, and sift out the finer flour, you're left with a coarser wheat flour called semolina. That's the flour from which they make couscous. The first step is known as hydration. An automated food processor measures about 1/3 water to 2/3 semolina, then mixes them for 3 minutes. The flour particles absorb the liquid and bloat into a raw dough. The dough particles then go into a rotating drum, where they spin for 7 minutes. This rounds them into balls of varying sizes. A screen inside the drum sifts out the big clumps. The raw dough balls go into a giant steam cooker for 15 minutes. The intense heat, 100 degrees Celsius, cooks the dough by gelatinizing the starch in the wheat. As the couscous balls exit the steam cooker stuck together, giant revolving blades break them up. The soggy couscous now enters a rotating dryer where it spins for 18 minutes. This removes 22% of the water. The remaining moisture is necessary to prevent the couscous from drying out in the package. As the couscous pours out of the dryer onto the conveyor belt that funnels it to the next station, you can see that the balls are much drier and relatively uniform in size. But they're still steaming hot, so they go off to a refrigeration chamber for 2 minutes to cool. As the couscous exits the chamber, it runs through a screening machine that separates the balls, called grains, by size. Medium and fine couscous go off to their respective storage silos, while grains that are too big or too small go back to be reprocessed. The couscous making process, from wheat semolina to the finished product, has taken just 45 minutes. As we've seen, most of the cooking's been done by the factory, so all the consumer will have to do is steam this ready-made couscous for just 5 minutes on the stove or in the microwave. This factory packages its couscous in bulk quantities as well as in smaller meal-sized portions. Today, ready-made couscous comes in many different flavors. And depending on the dish you're making or your personal preference, you can choose medium grain or fine grain. Plain or flavored couscous is becoming an increasingly popular side dish, an alternative to rice, potatoes, or noodles. You can even buy main course couscous kits that come with a can of vegetables and a packet of sauce. There's nothing little kids love more than digging their hands into a mound of squishy modeling dough, then rolling and shaping it. It's a hands-on experience in creativity, made all the more fun by modeling doughs that come in bright colors and yummy scents. Just in case little Billy decides to snack on his artistic creation, this scented modeling dough is made entirely of food ingredients, flavorings and colorings, salt, flour, hot water, and some secret ingredients the company won't divulge. The key to achieving just the right consistency is meticulous measurement. They use electronic scales to precision weigh each ingredient. Bit by bit, they pour the dry ingredients and flavorings into the mixer. The amount of hot water they add varies according to the color and scent they're producing. The proportions are about 30% water to 70% dry ingredients. The last ingredient is food coloring, in this case, cherry red. For the modeling dough to come out just right, the mixing time has to be precisely 3 minutes and 20 seconds. When the dough comes out, it's roughly the consistency of pie dough. It's quite hot from all that churning, 70 degrees Celsius to be exact, but there's no need to cool it before packaging. It goes right into a machine called the stuffer, which cuts it into container-sized portions. The finished product is soft and malleable enough for endless hours of play. Besides smelling delightful, this modeling dough doesn't crumble, doesn't stick to things, and won't stain clothes or upholstery. A machine called the container distributor lines up the plastic containers. Then the stuffer drops a wad of hot dough into each one. As the containers move down the line, on goes a cover stamped with the production date. A compression roller then runs over the cover to create an airtight seal. Last but not least, a colorful sticker to boldly identify the scent. The containers pass through a metal detector, a precautionary measure in case some metal shards wore off the machinery and landed unnoticed in the dough. The company lab is continually developing new scents. This brand comes in 36 different scents so far, from a variety of fruits to kid-friendly foods. The lab is also constantly experimenting with new colors, though some, such as purples, are quite difficult to produce. Children, of course, can make their own colors simply by combining existing ones. If you leave the modeling dough out of the sealed container for too long, it'll dry out. But because this brand is water-based, not oil-based like some others, you can revive it. All you have to do is add a few drops of water, knead it a bit, then put it back in the sealed container. After a few hours, your scented modeling dough will be as good as new. Wicker is thin branches or vines flexible enough to be woven. Many plants can be used for wicker, such as willow and rattan. Quality wicker is very durable. You can find antique wicker furniture that's as sturdy today as in its heyday. The oldest piece of wicker on record dates back to 1400 BC. Archaeologists discovered it in Egypt, where in ancient times people used wicker chairs. Hand-woven wicker furniture was the rage in Europe and North America in the 1800s. To meet this demand, trade schools churned out master wicker weavers. But by the 1930s, manufacturers developed a paper fiber to mimic the look of wicker and large mechanized looms to do the weaving. Today's genuine wicker items are usually made of rattan core, rattan palm tree branches stripped of their bark, then processed into different diameters and profiles. At this workshop, they use a manual loom to weave wicker hampers. Taking what's known as flat oval rattan core, flat on one side, rounded on the other, they run horizontal strands through vertical strands in an under and over pattern, working between the hamper's wooden frame and its fiberboard lining. They keep the vertical strands taut by tying them to weighted ropes. It's important to keep moistening the rattan with hot water to keep it supple enough to manipulate. They weave one thin round strand after every 13-centimeter high section of flat oval. There's no structural reason for this pattern, it's purely aesthetic. A wicker wastebasket begins with a base that dictates the shape. They insert vertical stakes of round rattan core along its perimeter. Then below the base, bend each stake over the next, then under the one after that. This forms what's called the foot border, a bottom rim that holds the base securely in place. Now they insert a wooden form and begin weaving. First, a small section of round rows, then a large section of flat oval ones. Slowly and patiently, they work their way to the top, never resorting to glue or staples to hold the strands together. Only a hook to compress the rows for a neat and tight weave. Every so often, they use pliers to tear off a stray fiber. Now for the finishing touch. They braid what's left of the vertical stakes into a decorative top rim. This particular braiding technique is very complex, requiring all 10 fingers and a special tool to pry stubborn strands apart. They snip off the excess with a cutter. When they're finished, they remove the modular wooden form. Its components are numbered so they'll know how to reassemble them for the next basket. Another more decorative way to finish the top of a basket is this arch technique. They trim each vertical stake, bend it into an arch, then tuck it into the basket 3 stakes over. This measuring tool ensures the arches are of equal height, while this metal device creates a space into which to tuck each stake. Wicker weavers create magnificent designs by combining various shapes and sizes of rattan. A strand can be as thick as a pencil or as thin as a needle. While this doesn't quite fall under the category of wicker, it's not uncommon to see wicker workshops use other natural materials. Here they're weaving a chair seat out of cord made from seagrass. There's also wicker seating material. This pre-woven sheet is called cane seating or rattan peel. It's made from the bark stripped off the rattan branch. First, they force it into a groove in the chair's wooden frame. Then they glue in what's called spline, a strip of rattan core with a pointed edge. They wedge that edge into the groove, hammering it down to hold the rattan peel in place. Then they trim off the excess. Because wicker is wood, it can be stained or painted, or left its natural color. Whatever the finish, they give it 2 or 3 coats of varnish for protection.